Hello students, welcome to my channel Sri Black's Edutainment. Right students, today we will discuss one most important topic, that is expectation and discrete distributions. This is of unit 2 of your probability and statistics. Okay, first we will see mathematical expectation, the definition of mathematical expectation. Let us see what is the definition. So let capital X be a random variable, then the mathematical expectation of X is denoted by capital E of X. Okay, mathematical expectation of capital X random variable. Capital X is nothing but a random variable. Random variable is denoted by capital E of X, and it is given by capital E of X is equal to sigma X into P of X in the case of discrete random variable. I think we have discussed what is discrete random variable, what is continuous random variable in the previous classes. So I'm not going to go details of the discrete random variable and continuous random variable. Okay, so if it is a continuous random variable, the definition is minus infinity to plus infinity, integral of minus infinity to infinity x into f of x into dx. Okay, so here p of x is equals to probability mass function of x. In the case of discrete random variable, we have probability mass function. In the case of continuous random variable, we have probability density function. So this P of x is called as probability mass function, and this f of x is called as probability density function. Okay, so this is the mathematical expectation of a random variable. If it is a discrete random variable, capital X is a discrete random variable, we calculate by using the formula or using the definition sigma x into P of x and minus infinity to infinity integration of x into f of x. Okay, this E of x is also known as the mean of the random variable. Okay, expectation, mean, both are same. So in the problem, if it is asked that find the expectation or also find the mean, we need to find expectation only. This we need to use this formula only, isn't it? Right. Now we go to the next one. So these are some definitions of an expectations. So what we have seen in the previous slide is expectation of a random variable. Now we see definition of mathematical expectation of a function. If a function is given, how do we define the expectation? Right? Mathematical expectation of a function. Right? We are considering g of x be any function of the random variable capital X. Then expectation of g of x. So what we have seen in the previous slide, expectation of x. So what is the difference? In the place of x, here g of x is there. Just replace in the place of x, g of x, we get the definition. Sigma x g of x into p of x. Where in the place of random variable, we get the function g of x, and p of x is the probability mass function. It does not change. So in case of discrete random variable, the expectation of the function g of x is sigma x g of x into p of x. And if it is a continuous random variable, the definition is integration minus infinity to plus infinity g of x into f of x into dx. Clear? So in case of continuous random variable, integration is there. In case of discrete random variable, we have g of x into p of x. Now in the place of g of x, that means a particular function, some particular functions are given. Then what is the expectation? We will see. G of x is equal to say x to the power of r. then expectation of x to the power of r equals to sigma x to the power of r into p of x. Just replacing the g of x with x to the power of r, we get the expectation of discrete random variable, and replace g of x by x power r for continuous random variable, integral minus infinity to plus infinity x power r into f of x into dx. It is a for continuous random variable. Now this is also called as mu r, mu r. So this is x to the power of r minus 0. So this is called about origin. If we move to the generalization of expectation, the definition is like this. Just to see. Yeah. So here we coming to the case 3 point of view. Let g of x is equals to x minus mu whole to the power of r. Then this expectation is called as rth moment of variable about x. Here about mean x minus mu. So in the place of g of x, we are considering x minus mu whole to the power of r. So this r stands for rth moment of the variable x or g of x of the function g of x. Rth moment about what we are finding here. The minus is tells tells us about mu. So we are finding the expectation of the function g of x rth moment of variable x about the mean. This is called central movement. Why it is called central movement? Central tendencies. What are the central tendencies? Mean, mode, median. These two are called central tendencies. So here we are finding the expectation of the function g of x about the mean. So we call it as central movement. Central movement, isn't it? Okay, the definition is same. Sigma x, if it is a discrete random variable, sigma x into x minus mu whole to the power of r, because we just replace x, capital X by x minus mu whole to the power of r in the basic definition. If it is a continuous random variable, integration of minus infinity to infinity x minus mu whole to the power of r, simply we replace capital X by x minus mu whole to the power of r into f of x into dx, right? So where this p of x is the probability mass function and f of x is the probability density function for the given random variable, right? Clear? Now if we want to find non-central moment, so if mu is there, then it is said to be the central moment. If mu is not there, say if we take any point in the domain of the random variable, then it is called non-central moment. Non-central moment, right? Non-central moment or rth moment of variable x about a point A. Rth moment of a variable x about a point. So we are finding the expectation about a point. We are taking x minus a whole to the power of r. So it is called rth moment of the variable about the point A, right? So it is denoted by mu dash r. In the place of A, if we take 0, we have discussed in the earlier case, x to the power of r, that is called mu dash r about origin. So A is the point 0. Then we call it as about the origin. So this is not about mean, it is a point. Therefore, it is non-central movement. Please observe that it is non-central movement, it is not the central movement. We are not finding about mean, we are finding about a point, right? So if we find about mean, then it is said to be the central movement. Clear? Now we are going to discuss some important properties of these central movements or non-central movements. So some important properties of expectations. Okay, we are going to discuss some important properties of expectations. Right. So there is a special case. If r is equals to 2, this expectation is said to be the variance. We denote it as mu 2. So in the previous about mean expectation, r is equals to 2, this is called variance. The expectation is said to be the variance. So E of x minus mu whole square is equal to E of x minus mu whole square into P of x. If x is a discrete random variable, minus infinity to infinity x minus mu whole square into f of x into dx. If x is a continuous random variable, we will discuss more about variance in the next slides. So now we are going to discuss some properties of expectation. So the first property or first theorem, this is the most important theorem, addition theorem of mathematical expectation. Let us state the addition theorem. If x and y are two random variables, then E of x plus y equal to E of x plus E of y. Nothing but expectation of x plus y is equals to expectation of x plus expectation of y. That means sum of variables expectation is equal to sum of their individual expectations, right? Provided all the expectations exist. Now we'll see the proof of this. So it is easy to prove in the case of continuous random variable, right? So we are taking continuous random variable. We are considering continuous random variable to prove this. We can prove by using in the case of a continuous random variable as well as discrete random variable, but it is easy to prove if it is a continuous random variable. So we are taking capital X and Y are continuous random variables, right? So let capital X and capital Y be two continuous random variables. So with joint probability density function. Why we call as the joint probability density function? Because here we are taking X and Y, two random variables, right? So find and marginal probability density functions are f of x and f of y. Joint probability density function is nothing but f of xy. This is the joint probability density function. F of x comma y is the joint probability distribution function, and f of x and f of y are the marginal probability distribution functions. You have to remember these two words, right? Then by the definition of mathematical expectation, what we have? E of x is equals to integration of minus infinity to infinity. In the case of continuous random variable, we know that expectation of x is equal to minus infinity to infinity x into f of x into dx. In the case of y, it is E of y minus infinity to infinity y into f of into dy. That means wherever we get integration of minus infinity to infinity x into f of x into x, we can write it as e power x, e of x. And wherever we get minus infinity to infinity y into f of y into dy, we get e of y. Now we see e of x plus y. E of x plus y is equal to, according to our definition, what is the expectation formula? E of x is equals to in case of continuous random variable, we have minus infinity to plus infinity x into f of x into dx. All we know that in the previous slide. Clear? This is the definition we discussed. Right here, in the place of x plus y, and this is two variables. It is involving two variables. So for two variables, we need to take double integration. For capital X, integration of minus infinity to infinity, and also for capital Y, minus infinity to plus. Because these are two variables. Two variables involve this expectation of, in the place of x, what is there here? X plus y. So we need to take capital X plus y into f of x comma y into dx into dy, because here we have two variables. So f of capital X comma capital Y is the marginal probability density function, right? Into dx into dy, because we are doing the integration with respect to minus infinity to infinity double integration, minus infinity to infinity double integration with respect to x and y. So dx into dy. Is it clear, all of you? Right. So e of x plus y is equal to integration of minus infinity to infinity, integration of minus infinity to infinity, x plus y of f of x comma y into dx into dy. Now we split these integration, right? So we multiply uh, x with f of x y dx dy and y with f of x y into dx into dy. So expanding the uh, integration, minus infinity to infinity, minus infinity to infinity, x into f of x y into dx into dy, plus minus infinity to infinity, minus infinity to infinity, y into f of x into dx into dy. Now I am taking out this x from one integration, x of minus infinity to infinity f of x y into dy whole dx. Like that, here I am taking out y. Y. Alexa, stop. Y into f of x y dx into dy. Right? Now here, minus infinity to infinity f of x y into dy. What is it? Yes, here we are doing integration with respect to dy. So while doing integration with respect to y for the two variable function, one variable treated as constant. Say for example, if I am doing integration 0 to 1 xy into dy. So now I am doing with respect to y. So I clearly treat x as a constant. Say for example, I am doing the double integration, integral 0 to 1, integral 0 to 1 xy into dy. So I am taking y out, sorry, x out and y into dy. What is the integration of y? Y square by 2. Now if I substitute limits, what I get? In terms of x, a constant I get. That means what I get? 0 to 1 x into 1 by 2. I am taking 1 by 2 out into dx. That means total function in terms of x. Total function changes in terms of only x variable. So you can call it as f of x, right? So this function is only x, involves x steps. So we can take it as x. That means after integration of minus infinity to infinity f of x y into dy with respect to y, we get it as only x function. So we are writing here f of x into dx. Similarly, if we do integration with respect to x, then the function changes to y in terms of y. So we are writing here f of y into dy. Clear? So the integration of f of xy with respect to x changes f of xy into only fy function. That means opposite. and the integration with respect to y changes f of xy into only x function. So we are writing f of x. Clear? Now if you observe, minus infinity to infinity x into f of x into dx. This is by the definition of expectation, we can write it as e of x. And minus infinity to infinity y into f of y. Yes, by the definition of expectation, we can write it as e of y. So e of x plus y is equals to e of x plus e of y. Is it clear, all of you? So this is the uh, addition theorem on expectation. It is very, very important, right? Now we see one definition before going to discuss what is multiplication theorem on expectation. This is we need to know independent random variables. So random variables means x and y are said to be independent if the joint probability density function of x and y can be written as the product of marginal densities of x and y. Clear? The joint probability of x and y can be written as the product of the marginal density functions of x and y. Then x and y random variables are said to be independent. Clear? So that means f of x comma y, this is the marginal density function. It can be written as f of x into product of the marginal probability density functions, right? The joint probability density function f of xy is the joint probability density function. Joint probability density function can be written as the product of the marginal probability density functions f of x into g of y. Then capital X comma capital Y are said to be the independent random variables. Okay, based on this our uh, product theorem is there, right? So we will discuss the product theorem in the next video. So thank you all for listening this class, right? So we will clear. Uh, we are going to leave now. Thank you guys. So this is very, very important theorem, right?